This is chapter 18, number 68, and I think that you should pause right now and reread this question if you haven't done it recently. There's a lot going on here in terms of the wording. The key thing is that these two spheres are hung from a common point. So you have two objects, okay, and 2-point charges, or what we're going to treat as 2-point charges. And initially, they just hang straight down and there's no charge. You give them a charge, they're going to repel each other, and they're saying that they will swing up to some point, kind of like an electroscope, but not exactly the same. I'm going to draw the after picture. So common point. So here's the point in the ceiling where they're hanging from. Here's one sphere. Here's the other sphere. And they said that the angle that they spread apart to is 36 degrees between the threads. So you got to be real careful on what that angle is. This is your 36 degrees, not 360. That is your 36 degrees right there. Okay? I'm going to draw a bigger version of that over here, but let's talk about the forces that are acting on this. There's going to be tension, and we're going to have free body diagrams. There's going to be tension going in the direction of the string. Tension on this one as well. Weight down, because they gave you a mass, weight down. And then the electrostatic force will be the repulsive force. So you're going to have a force of the electrostatic, or excuse me, due to the other charge, to the left on this one and to the right on this one. That's why they swing apart. Lots going on. I'm going to draw a triangle over here to help me with this problem. And I meant to make this a little bigger, so let's extend that. Okay, and there's a couple things you got to be careful of, just like in prior chapters, is that when you're doing stuff with the triangles and getting components and things like that, don't mix your meters and your newtons. Either just deal with the stuff that's in meters and your distances and stuff like that, or just deal with the newtons. I'm going to put information for the distances on here, but then we'll use a similar triangle for our forces. I'm going to drop a bisector right here, because I like right triangles, and we're going to need that. Okay, so this is meeting in a right triangle. And if this whole thing is 36, that means each one of these, this is not drawn to scale, because this looks like it's another 90 degrees. I apologize. That's not right. Okay, but this will be 18, and this will be 18. So we got a 90 and 18, 18, not drawn to scale at all. And they told us the lengths of the threads. So that'll be this distance, which is 0.25 meters. We're doing some geometry / trig stuff here. 0.25 meters. And then also, when they were hanging straight down, okay, that would have been when they were here, because they've swung up to this point. So we also have that this distance right here, this dotted line, is also 0.25 meters. Don't really need it because I have, wait, is that right? No, that's not right. I apologize. Ignore that. Okay. We have the 18 degrees. We have the 0.25 meters. We can get the other two sides. This is a right triangle now. This is not the same length as this. Okay. I'm thinking about a different problem where we'd have had a dotted line here, and don't worry about it. Okay. And we're trying to find the charge on the ball and the tension in the thread. So we're looking for charge and tension. Well, tension is a force, so that leads me towards free body diagrams. And charge, if we're looking for the charge on here, probably we're going to be using F equals K Q1 Q2 over R squared. So let's start drawing free body diagrams for one of these. I'll just pick the one on the left, and we'll start there. So force of tension, force of weight, and the electrostatic force to the left. Okay, and I'm just going to start summing forces. These are suspended at this point. So when I sum forces in both directions, it'll be equal to 0. So I'll have force of E, call up and write positive, so negative force of E, and then tension in the X will be to the right, so FTX equals 0. That's what's going on in the X direction. In the Y direction, we'll have tension in the Y going up, and then weight going down equals 0. And now we're at the point where, believe it or not, you could probably solve for a lot of this if we can get this distance between the charges, so we can get this FE. And since that's, are we given the charge? No, we're looking for the charge, okay? So we're stuck here because we don't know FE and we don't know tension. So let's start in the Y. Let's plug in what we know here. So for the weight, we're given the mass, which is 8.0 times 10 to the negative 4th kilograms times 9.8. So just mg there. Got my negative on there already. And I can get my tension in the Y direction. Whatever that is. Let's see here. 8 times 10 to the negative 4th times 9.8. And we get 0.00784. Obviously not doing sig figs here, scientific notation. It's okay for the AP test, reasonable number of digits, all that good stuff. So we have tension in the y. If we have tension in the y and we have an angle, do not use the 0.25. I'm talking about a force now. If we have tension in the y and this angle, we should be able to get tension in the x. Because up here, if I draw my, show you this, here's my force of tension. Here's what my tension in the x would look like. Here's my tension in the y. We have similar triangles. This triangle are similar. That means this is 18 degrees, and we can relate the x to the y. You could use tangent to relate the x to the y directly and get tx, or you can do the substitution with t cosine theta, t sine theta. I think I'm going to go ahead and do the tangent again. I've done this in a prior problem. It's just another way to attack these problems. But you could, what I'm talking about is you could, let's see here, fty, this is the adjacent side. Yeah, this is the adjacent side. So you could write here ft cosine theta. So if you wanted to, this is the other way, ft cosine theta right here. And up here you could put an ft sine theta and keep going. I'm not going to do that. I'm going to do it a slightly different way, and I'm going to write tan theta. Looking at my triangle here is opposite, which is ftx, over adjacent, which in this problem is fty. And I know fty and I know theta, so I'm going to get my ftx. And then I'll go back over here. So tan of 18 degrees equals ftx over 0.00784. And let's get that x component. By the way, anytime you have an angle and you have one of the components, either x or y, you can use this idea to relate them. You just check your triangle, make sure you've got these the right way, but it'll always be tangent. It's just a question of which one's over which one. All right, so tan of 18 times 0.00784, getting 0.00255. Let's keep the number digits there the same, or another significant digits there the same. So 0.00255 newtons is my Tx. I can get my Fe. We're supposed to find the tension as well. So at some point now I could use this, or I could do Pythagorean theorem, whatever, to get force of tension. Let's go ahead and do Pythagorean theorem. So force of tension will be square root of these two things squared. So 0.00255, I know I'm writing small, squared plus square root of, square root of 0.00784 newtons squared, and then the square root of, let me rewrite that. Do that down here. F tension equals, just give you the formula, Ft x, tension in the x squared, plus Fty squared. There you go. And we have Tx and Ty. You can convince yourself that works out. I will check the answer for Fe, and that'll let me know if I've made any algebraic mistakes. So now we go back here that we have Ftx, and we can say Fe equals 0.0025 newtons, because we have this. So just solve for Fe. So 0.0025 newtons. And now we can get our charge. Because I believe, let me just double check here, they are given identical positive charges. So they have the same charge. So when I'm applying this K, Q1, Q2 over R squared, these Q's will be the same, similar to the previous problem on YouTube. So I'm going to write this as K, Q squared over R squared. This will not always be the case. This is just because Q1 and Q2 are the same. So I'm just going to call it Q. So both of these, I'm going to get rid of those subscripts. Both of them we're just calling Q. All right. So we got our 0.025 newtons equals, I'm just going to leave it as K. It's 9 times 10 to the 9. Q squared. And now the part where we're stuck is R. So now we have to go back and get the distance between them. So that is this entire distance. So it's this whole thing. I like my right triangle here, so I'm going to go ahead and just get this side based on this bit of information, since I already have that set up. So this will be the opposite. Then I have the hypotenuse. So a little scratch work here. Sine of 18 degrees equals the opposite. I'll just label this x over the hypotenuse, which is 0.25. And I'm going to get an answer for x. Sine of 18 times 0.25 0.0773 meters. But that is not the distance between them. We need the whole thing, so I'm going to double it. So from here to here is 0.15, call it 5 meters. So down here, 0.155 meters squared. And let's do all the math on my calculator here. Add steps if you need to. 0.0025 times 0.155 squared. Move that over. And then divide by k. 9 times 10 to the 9th, about. And then take the square root or raise it to the 1/2 power. Same difference. And I'm getting a charge of, I'm going to write it down here. I'm getting a charge of about 8.17 times 10 to the negative 8 coulombs. Well, I hope they got that. Let's see. Oh, yeah, they did. Okay. I was looking at the wrong problem. They got 8.2. I got 8.17, so we're good. And then to get the tension, you can continue this on your own. Okay. You can plug in FTX, which I know is right now, and you can plug in FTY. Okay, I know these are both right, because otherwise this would not have worked out correctly. Plug into here, and you can get tension. So just do the Pythagorean theorem to finish it off. If you have questions, there's a lot going on here. If you have questions, feel free to stop by after school.